So this is the Photonic Toroidal Vortex model, and what you shall learn in the next few minutes is how to carry out the hydrogen atom hyperfine level calculations using this model. What we can see in this picture are two toroids, the red one, which is the proton, and the purple one, which is the electron. The toroid is really a trapped photon with three nested rotations. The first rotation is circular polarization, which is called SP1 in this model. If you rotate the axis of that around a guide tube, you get poloidal rotation, SP2, which is optical orbital angular momentum. And if you bend the axis of that into a toroid, you get what's called SP3 rotation in this model, which is toroidal rotation. Fields are generated by the rotating photon. The poloidal rotation generates a magnetic momentum field, and the toroidal rotation creates an electric momentum field, which is perpendicular to the magnetic one. And they initially propagate at the speed of light. Okay, so let's go straight to some data. This is the 2s hydrogen atom state. The main data for these calculations comes from Horbach and Hessel's 2016. Here is their value for the hyperfine midpoint, and this is the PTV value. And this is their value for the hyperfine half shift, and this is the PT value. Now, if you were doing a quantum electrodynamics calculation, you would aim for the hyperfine centroid, which is the weighted average of the levels here. The midpoint value takes a value halfway between them. That's called the hyperfine midpoint. And then you do a hyperfine half shift each side of this. A quick review of how the QED calculation works. You first calculate a fine structure value. What this is, it's the rest mass of the electron minus the fine structure energy of the electron, which is actually greater than the rest mass, which means you're going to get a negative value. But here we take the magnitude, which is why this bottom value is positive. And this also includes the reduced mass. If you want to strike the experimental hyperfine centroid, you have to calculate something called the Lamb shift, which in quantum electrodynamics is a very complicated calculation, which involves at least 6 correction terms. In contrast, the PTV calculation goes for the hyperfine midpoint, which, as we shall see, is a 2-term calculation, and then does a hyperfine split, an equal hyperfine split each side of that. Here is the PTV 3-term calculation. 2 of the terms give you the midpoint, and then we get the up and down half shift. So the Coulomb potential, which is a rotational field generated by the proton, displaces half the electron toroid's rotational energy into translational energy. And once the electron, which is approaching the proton along the same axis, once it gets to the bound state distance, this translational energy is emitted, radiated away as ionization energy. So it's ionization energy to infinity. It's a 2-part calculation for the midpoint. You want nu 3D and nu mag. The first one is the modified fine structure term, and the second one is a magnetic potential. Let's take a look at those. Here is the PTV fine structure formula. It looks a bit different from the Sommerfeld-Dirac version, and the reason for that is this one uses an internal potential. It doesn't use the Coulomb potential to get it, and the internal potential in terms of the structure of toroidal dynamics is basically a toroidal rotation. So you can calculate discrete energy levels with an internal potential. What the Coulomb potential does is move rotational energy out of the electron into translational energy, so it modifies those discrete energy levels, but it doesn't cause them. What we're going to do now is take this fine structure formula, and where we see alpha squared, we're going to replace it with alpha squared d. Now, d is a speed adjustment term. It's over here, and you can see it contains the parameter gamma, which we're going to be exploring in more detail later. This is the reduced mass part. It's the relativistic, electron relativistic reduced mass part. Here's the electron rest mass. Here's the proton rest mass. So that's the calculation for the adjusted fine structure. Now we come to the magnetic potential, which is the second term in the hyperfine midpoint. You'll see D2 bar here, which we saw on the toroidal diagram. This is the bound state distance. This is calculated from the condition that the Coulomb potential energy, which intrudes in the electron toroid, is equal to the remaining electron rotational energy. So if you satisfy that condition, you're at the bound state distance, and here are the calculated bound state distances. They're actually expressed as fractions of the electron toroidal radius, R30, which is constant for all states. What does vary is the bound state distance. The toroidal radius stays the same. And so these values appear to be varying as 2n. Also, as well as the bound state distance, we've got two parameters, A and B. B is in the power and A is a multiplier. So let's take a look at those parameters in more detail. A, B, and gamma. Gamma appears in the D function in the speed adjustment to the fine structure term, and A and B appear in the magnetic potential. Now these three parameters are locked on the first three states of a spectroscopic series. So for the NS half series, they're locked on 1, 2, and 3. They have to work by themselves for the rest of the states in the series. So for n equals 4, n equals 5, 6, so on, they have to work unadjusted. And that's the case with all the spectroscopic series. The parameter set is locked on the first three states, and then they have to work on the rest of them. How do we determine these parameters? What we do is we vary gamma, and what we're looking for is that the value of B across the first three states, when we try to line up with the experimental hyperfine midpoint, the value of B remains consistent. That means there's minimum error between them. If you impose that condition, what comes out of that are two solutions, one with gamma greater than 0 and one with gamma less than 0. And it turns out that across all states of the series, B is equal to -3. Now, if we look at the diagrams below that for the blue shift and the red shift case, B turns out to be -3 in both cases across all series. But there's something quite remarkable comes out of this parameter search. The value of A over gamma tends to some constant across all spectroscopic series. We now take a look at the hyperfine half shift. This is a formula that works across all spectroscopic series. Notice there's a parameter k in here. K equals 1 for the NS half series, which means there's no adjustment at all. And then for NP half, it's a third, and so on. You can actually calculate the k parameter by altering the eccentricity of the electron colloidal circuit. If you alter the eccentricity, you're altering its receptivity to the proton's magnetic momentum field. And so you can reproduce these values of K. We've got some visualizations here of how these calculations are working. As I said, there are two cases. There's a case gamma less than 0 and gamma greater than 0. If you've got gamma less than 0, A turns out to be bigger than 0, opposite sign. And if you've got gamma greater than 0, A is less than 0, opposite sign. So you start off the calculation with the first fine structure formula I showed you. You include a reduced mass, you include the d speed correction with the gamma parameter, and then you end up with the adjusted fine structure frequency in megahertz. And now if you add the magnetic potential term, which with A bigger than 0 is a blue shift, you come down, you actually increase in frequency going down the diagram to the hyperfine midpoint. The other alternative is to start again at the unadjusted fine structure formula. When you have the d function included and the reduced mass included, what happens is you increase in frequency, and then when you put the magnetic potential term on it, you end up at the same hyperfine midpoint as before. So we've got two ways to get the hyperfine midpoint. And when you come to the third term of the calculation, which is the half shift, you'll notice there's a blue shift here and a red shift here, and they've got the same magnitude each side of this midpoint. When the magnetic potential is a blue shift, the half shift is a blue shift. When the magnetic potential is a red shift, the half shift is a red shift. And what's controlling these shifts are the relative rotation sensors of the proton and electron toroidal circuits. When they're rotating in the same direction, you get red shifts, and when they're rotating in opposite direction, you get blue shifts. And what's happening is the proton toroidal circuit is generating a magnetic momentum field, which is cutting the electron toroidal circuit. And so the direction of rotation turns out to be crucial. Let's take a look at some data. This is hydrogen atom hyperfine midpoint data. We've got pairs of numbers here. The top one is the experimental value, the bottom one is the PT value. So as I said, the parameters A, B, and gamma are lined up on the first three terms of a spectroscopic series, which is why we get the perfect answer. What's crucial are the next terms, because the parameters are unadjusted for these, and we can see quite good agreement, sub-megahertz agreement. The NP half series, the parameters are lined up on the first three terms. So do the values work for the next terms, or the next three terms? That's quite good agreement, and so on. We line up on the first three terms, and then we have to have agreement on the next terms. That's the blue shift case. Exactly the same for the red shift case. Line up on the first three terms, and you have to agree on the rest of them. The third term of the calculation half shift data. So all the NS half data is with the parameter k equals 1. Not such a good agreement here, but the rest of them, that's quite good accuracy. And as you can see, as we go to the higher spectroscopic series, we get some very good agreement on the half shift data. If you want the full hyperfine splitting, you have to double these values. So the 1S half full splitting is 420.4058 megahertz. Now, this model also applies to deuterium. The same investigation into these parameter values has been carried out for deuterium. And what we find is B is again -3. Now, B is the parameter in the magnetic potential, and with a -3 power, that appears to suggest a dipole-dipole interaction. The other thing to point out is the value of A over gamma, which across the blue and red shift case and the spectroscopic series, they appear to be heading for the same value. Let's take a look at the deuterium midpoint data. Not so accurate here. We've got about 8 megahertz error. We've got 4 megahertz error here, 4 megahertz here. And there's probably some additional term needs adding to this. Hydrogen, you've got 1 proton. Deuterium, you've got a proton and neutron. There's probably some additional term which would take care of these errors, so that would need further investigation. So I pointed out the constancy of A over gamma for hydrogen and deuterium. So an exploration has been made into hydrogen, deuterium, tritium, 3 helium and 7 lithium, hydrogenetic atoms. And this formula here, these are the results it predicts. And what comes out of the PTV investigation are these values. And you can see the errors are much less than 1%. If you'd like some further information on this PTV model, you can visit barrierspuzzle.com/physics, where you'll find a Python program which contains the complete calculations, which you can check at your leisure. The data output is available there. We've got peer-reviewed papers which show the foundations of this model. We've got preprint papers on how this can be applied to the Lorentz force deflection. There's a mechanism, a toroidal dynamics, which will predict the deflection. The theory has been applied to Bose-Einstein statistics with distinguishable photons. And if you want to interrogate this model in great detail, you could go to an AI system like ChatGPT or Gemini or Meta or Claude. And if you give it the link barrierspuzzle.com/physics07, it will be able to assimilate all the details of the model incredibly quickly and answer your questions in great detail. So that's the hyperfine calculation for the hydrogen atom. That's how the PTV model handles it. And I hope this has inspired you to explore the model in more detail. So thank you very much for listening.